Emotion and cognition have traditionally been regarded as separate domains within psychology and neuroscience. Yet modern research increasingly reveals that they are deeply interconnected processes. This interdependence shapes virtually all aspects of human experience, from perception and attention to memory, decision-making, and social behavior. Far from being opposing forces, emotion and cognition work synergistically, often co-constructing our subjective reality and adaptive responses to the world. To understand this relationship, it is important to first delineate what is meant by emotion and cognition. Emotion refers to complex physiological and psychological states that involve subjective experience, expressive behavior, and arousal. Emotions often arise in response to significant internal or external events, serving as a rapid signaling system that helps organisms prioritize action. Cognition, on the other hand, refers to mental processes involved in acquiring knowledge and understanding through thought, experience, and the senses. It includes processes such as perception, attention, learning, memory, reasoning, and language, although distinct in their definitions. Both systems rely on overlapping neural circuits and interact dynamically throughout the brain. Neuroscientific studies have provided a compelling framework for understanding the neural integration of emotion and cognition. The amygdala, a small almond-shaped structure in the medial temporal lobe, has been widely studied for its role in emotional processing, particularly in fear and reward learning. However, the amygdala does not operate in isolation. It is highly interconnected with the various cortical regions, especially the prefrontal cortex, FC, which is traditionally associated with higher order cognitive functions such as planning, inhibition, and working memory. The reciprocal connections between the amygdala and PC exemplify the bidirectional influence emotion and cognition exert on each other. For example, the ventromedial prefrontal cortex (VMC) modulates emotional responses by integrating contextual information, allowing us to interpret and regulate emotional experiences in adaptive ways. This neural interplay has significant implications for memory formation. Emotionally salient events are often remembered more vividly and with greater accuracy than neutral events, a phenomenon known as emotional enhancement of memory. This effect is largely attributed to the modulatory influence of the amygdala on the hippocampus, a key region for memory consolidation. When an emotionally charged event occurs, the amygdala activates the hippocampus and associated neuromodulatory systems, such as the release of norepinephrine and cortisol, which strengthen synaptic connection and make the memory trace more robust. While this mechanism enhances survival by prioritizing emotionally relevant information, it also has downsides, such as the formation of intrusive memories in post-traumatic stress disorder, PTSD. Emotion also shapes attention, often acting as a spotlight that prioritizes processing of emotionally relevant stimuli. This can be seen in the attentional blink paradigm, where emotional stimuli are more likely to be detected than neutral ones within a rapid stream of visual information. Similarly, individuals are quicker to orient to emotionally charged stimuli, such as angry faces, a tendency that likely evolved to facilitate threat detection. However, the emotional bias in attention is not always adaptive. In anxiety disorders, for instance, individuals exhibit hypervigilance to threat cues, which may impair performance on neutral or positive tasks and contribute to a cycle of negative appraisal and emotional dysregulation. The influence of emotion extends to decision-making, particularly under conditions of uncertainty. The somatic marker hypothesis, proposed by Antonio Damasio, posits that bodily-based emotional signals guide decision-making by marking certain options as more or less advantageous based on prior experiences. These somatic markers operate largely below conscious awareness, but are vital for complex decision-making, especially in socially nuanced or ambiguous situations. Lesions to the vamphy, which disrupt these emotional cues, often result in impaired judgment, even when cognitive reasoning remains intact. This has been illustrated through gambling tasks in patients with vamphic damage who fail to learn from negative outcomes and persist in making disadvantageous choices. Cognition can also regulate emotion, a process known as cognitive reappraisal. This strategy involves changing one's interpretation of a situation to alter its emotional impact, and it engages lateral and medial regions of the facet to exert top-down control over the amygdala. Reappraisal has been shown to reduce negative affect, decrease amygdala activation, and enhance psychological well-being. This capacity is central to emotion regulation and underlies various therapeutic approaches, including cognitive behavioral therapy, which teaches individuals to identify and modify maladaptive thought patterns that contribute to emotional distress. Social cognition is another area where the emotion-cognition nexus is vividly apparent. The ability to understand others' emotions, often termed emotional intelligence, involves both affective empathy, feeling what others feel, and cognitive empathy, understanding what others feel. These skills are essential for effective communication, cooperation, and conflict resolution. The mirror neuron system, which activates both during action execution and observation, is believed to facilitate the simulation of others' emotional states, enabling a kind of embodied cognition that blends affective resonance. Deficits in this system have been implicated in conditions like autism spectrum disorder, where challenges in emotional and cognitive empathy can impair social functioning. Individual differences in temperament, personality, and developmental experiences further modulate the interaction between emotion and cognition. For instance, people with high trait anxiety often exhibit cognitive biases toward threat-related information, which perpetuates anxious affect and cognitive distortion. On the other hand, individuals with greater emotional granularity, the ability to precisely label and differentiate emotional states, tend to show better emotion regulation and cognitive flexibility. These findings suggest that the richness of emotional knowledge itself can enhance cognitive performance and adaptive behavior. Developmentally, the integration of emotion and cognition evolves over time. In early childhood, emotional responses often dominate behavior, with limited cognitive control. As the brain matures, particularly the facet, children develop improved executive functions and emotion regulation ability. Adolescence is marked by heightened emotional reactivity due to a mismatch in the maturation timeline of limbic and prefrontal regions, which can contribute to risk ability. By adulthood, emotion and cognition are more finely balanced, although this balance may shift again in aging, where declines in cognitive function can influence emotional processing and regulation. In sum, the once separate realms of emotion and cognition are now understood to be deeply interwoven, both in the architecture of the brain and in the fabric of human behavior. They interact in complex, bidirectional ways to shape perception, attention, memory, decision-making, and social interaction. Rather than competing forces, they are complementary components of the mind's adaptive machinery. Recognizing this integration has profound implications, not only for understanding psychological functioning, but also for designing interventions in mental health, education, and social policy. As science continues to unravel the nuances of this relationship, it becomes increasingly clear that to fully understand cognition, one must consider the emotional context in which it operates. Let's observe. Dual process theories in cognitive psychology and neuroscience represent a significant paradigm for understanding how humans process information, make decisions, and regulate behavior. These theories propose that our cognitive processes operate through two distinct systems, commonly referred to as System 1 and System 2. System 1 is typically characterized as fast, automatic, intuitive, and often unconscious, while System 2 is slow, deliberate, effortful, and conscious. This duality provides a compelling framework for interpreting a wide range of phenomena, from everyday decision-making to complex reasoning tasks. While these systems operate in parallel and often cooperatively, they can also come into conflict, especially in situations where intuitive responses produced by System 1 clash with the more rational calculations of System 2. The appeal of dual process theories lies in their explanatory power. They help clarify why humans sometimes make decisions that seem irrational or suboptimal, and how cognitive biases and heuristics can influence judgment. System 1 is evolutionarily older and is shared with many non-human animals, reflecting basic processes like associative learning, pattern recognition. It enables humans to respond quickly to environmental stimuli, a feature that is advantageous in situations requiring immediate action. For instance, recognizing a facial expression of anger or detecting a potential threat occurs almost instantaneously and without deliberate thought. These automatic responses are the result of mental shortcuts or heuristics that System 1 employed. However, this efficiency comes at a cost. System 1 is prone to errors and cognitive biases because it relies on limited information and context. Common examples include the availability heuristic, where people judge the likelihood of an event based on how easily examples come to mind, or the representativeness heuristic, where judgments are based on how much something resembles a typical case rather than on actual probabilities. System 2, on the other hand, is associated with more complex and abstract forms of thinking, such as reasoning, planning, and problem-solving. It requires significant cognitive resources and is engaged primarily when individuals are confronted with novel, difficult, or non-routine tasks. System 2 overrides the automatic responses of System 1 when it detects a mismatch between intuition and logic, or when a task requires sustained attention and critical thinking. For example, solving a complex math problem or evaluating a legal argument involves deliberate and conscious processing indicative of System 2. Importantly, System 2 is not infallible. It can be sluggish, subject to fatigue, and heavily influenced by motivation and cognitive capacity. Nevertheless, it is indispensable for tasks that demand rational deliberation and long-term planning. One of the most influential dual process models is the one proposed by psychologists Keith Stanovich and Richard West, which was later popularized by Daniel Kahneman in his seminal work Thinking, Fast and Slow. In this model, System 1 corresponds to Type 1 processes and System 2 to Type 2 process. Kahneman emphasizes how much of our daily functioning relies on the effortless processes of System 1, with System 2 acting more as a monitor or arbitrator that steps in under certain conditions. This framework sheds light on phenomena such as cognitive illusions, where System 1's intuitive judgments can be compelling yet incorrect, necessitating intervention by System 2 for accurate analysis. A classic example is the bat and ball problem, in which an intuitive but incorrect answer arises immediately, while a correct solution requires careful, deliberate reasoning. Beyond individual decision-making, dual process theories have broad implications for understanding social behavior, moral judgment, and even political reasoning. In moral psychology, for instance, research by Joshua Green and colleagues has shown that emotional responses aligned with System 1 often dominate in personal moral dilemmas, while impersonal or utilitarian judgments engage the more analytical System 2. This suggests that our moral evaluations are not solely the product of abstract reasoning, but are deeply intertwined with automatic emotional processes. Similarly, political attitudes and ideological beliefs have been shown to reflect the interplay of intuitive and reflective processes, with motivated reasoning often stemming from the effortful deployment of System 2 in service of prior beliefs and identity. Despite its explanatory appeal, the dual process framework has not been without criticism. Some researchers argue that the strict dichotomy between two systems may oversimplify the complexities of cognitive functioning. Critics suggest that rather than two discrete systems, cognition might operate along a continuum of automaticity and control, with processes varying in degrees of effortfulness and awareness. Others question the consistency and clarity with which System 1 and System 2 are defined and distinguished across different studies. Furthermore, some neuroscientific evidence suggests that the brain does not neatly segregate these functions into separate modules, but rather engages overlapping networks depending on task demands and context. Nonetheless, many proponents of dual process theories acknowledge these limitations and view the framework as a useful heuristic rather than a literal depiction of brain architecture. Recent developments in computational modeling and neuroscience have sought to refine dual process accounts by integrating them with theories of predictive processing and Bayesian inference. These models propose that the brain continuously generates predictions about the environment and updates them based on incoming sensory data. Within this framework, System 1 can be conceptualized as relying on fast, low-level predictive models, while System 2 engages higher, order representations to resolve uncertainty and correct errors. Such perspectives not only provide a more unified account of cognition, but also bridge the gap between psychological theory and neural mechanism. Moreover, this synthesis has practical implications for fields such as artificial intelligence, education, and behavioral economics, where understanding the balance between automatic and reflective processes can inform the design of interventions and systems. In educational settings, recognizing the limitations of intuitive thinking can lead to pedagogical strategies that promote deeper engagement with System 2 processes. Encouraging students to reflect on their reasoning, question assumptions, and practice metacognition can help counteract the biases of System 1. In behavioral economics, insights from dual process theories have inspired nudges, subtle changes in the environment that leverage automatic processes to guide behavior in beneficial directions without restricting choice. For instance, default options in organ donation, policies, or retirement savings. Plans exploit System 1's tendency to go with the status quo, thereby improving outcomes through minimal intervention. Ultimately, dual process theories offer a nuanced and dynamic view of the human mind, emphasizing the interplay between speed and accuracy, intuition and reasoning, automaticity and control. While the distinctions between System 1 and System 2 are not always clear-cut, they provide a valuable lens for understanding how we think, decide, and act. Whether in daily choices or complex moral deliberations, this framework highlights the importance of cultivating awareness of our cognitive processes and fostering conditions that support thoughtful, informed decision-making. As research continues to evolve, future iterations of dual process theories will likely incorporate more sophisticated models of cognition that account for variability, interaction, and contextual influence, thereby enriching our understanding of the architecture of thought. Reasoning, as a fundamental component of human cognition, is the process by which individuals draw conclusions, make decisions, and construct beliefs based on available information. Among the most critical forms of reasoning are deductive and inductive reasoning, each with distinct structures, applications, and implications for knowledge acquisition. Deductive reasoning begins with general premises assumed to be true and progresses logically to reach a certain conclusion. In contrast, inductive reasoning moves from specific observations to broader generalizations and theories, embracing a probabilistic nature rather than absolute certainty. Both types are indispensable in various intellectual pursuits, from scientific inquiry and philosophical argumentation to legal analysis and everyday decision-making. Deductive reasoning is often exemplified by syllogistic logic, a method formalized by Aristotle and further refined through centuries of philosophical and mathematical development. A classic example is the syllogism, all humans are mortal. Socrates is a human, therefore Socrates is mortal. This form of reasoning is valid if the conclusion necessarily follows from the premises are themselves true. The power of deduction lies in its capacity to provide certainty, provided the initial assumptions hold. This logical structure underpins mathematics, formal logic, and much of scientific theory testing, where hypotheses are derived from established laws and tested against empirical data. Deductive reasoning is inherently conservative, in the sense that it does not expand knowledge beyond the premises, but rather clarifies and explicates the implications of what is already accepted. Inductive reasoning, on the other hand, is fundamentally ampliative. It allows for the generation of new knowledge by identifying patterns, trends, or regularities in specific instances and generalizing them to form broader conclusions. For example, observing that the sun has risen in the east every day in recorded history leads to the general belief that the sun always rises in the east. However, unlike deduction, inductive conclusions are inherently uncertain. They are probable rather than definitive. This probabilistic nature is both a strength and a limitation. It enables the formulation of hypotheses and theories that can guide further investigation. But it also means that such conclusions remain open to revision in light of new evidence. Induction is the backbone of the scientific method's empirical component, where repeated experimentation and observation form the basis for theoretical generalization. The philosophical underpinnings of these reasoning forms reveal a historical tension between certainty and empiricism. Rationalist traditions, such as those championed by Descartes and Spinoza, elevated deductive reasoning, favoring it for its logical rigor and independence from sensory experience. Empiricists like Hume, however, underscored the role of inductive reasoning grounded in observation, questioning whether any knowledge could be truly certain outside the scope of empirical verification. Hume, in particular, challenged the justification of inductive there is no logical necessity, ensuring that future events will resemble past ones, a problem now known as the problem of induction. This critique exposed a foundational issue in epistemology and prompted subsequent philosophization of scientific falsification. Despite their philosophical distinctions, deductive and inductive reasoning often operate in tandem within practical and academic contexts. Scientific inquiry, for instance, is a cyclical process involving both. Hypotheses are deduced from theoretical frameworks and tested through inductive analysis of experimental data. Legal reasoning also exemplifies this interplay. Judges may apply general laws deductively to specific cases, while also considering patterns from past rulings inductively to inform judicial interpretation. Similarly, in artificial intelligence and machine learning, deductive logic may structure algorithms, while inductive learning from data patterns enhances adaptive capacity. These examples illustrate that rather than being mutually exclusive, deductive and inductive reasoning are complementary tools for navigating complex problems. Moreover, the cognitive processes underlying these reasoning modes are central to understanding human intelligence and decision-making. Psychological research has revealed that individuals often use heuristics or mental shortcuts that resemble inductive reasoning, which, while efficient, can lead to biases such as confirmation bias or the representativeness. Conversely, deductive reasoning tends to require more deliberate cognitive effort and is thus more susceptible to breakdowns when individuals lack the necessary logical training or contextual understanding. Educational systems aiming to develop critical thinking must therefore cultivate both deductive logic and inductive insight, training students not only in formal argumentation, but also in the evaluation of probabilistic inference. In sum, reasoning through deduction and induction constitutes the intellectual scaffolding of human inquiry. Deductive reasoning offers clarity and precision, deriving conclusions that are logically certain if based on true premises. Inductive reasoning, while lacking in logical certainty, provides the flexibility and openness necessary for discovering new knowledge through experience. Each serves distinct yet complementary roles in disciplines as varied as science, philosophy, law, and education. A comprehensive understanding of reasoning thus entails not only mastering the mechanics of both deductive and inductive logic, but also appreciating their interplay and limitations within broader epistemological framework. By honing our reasoning skills, we enhance our capacity to think critically, solve problems, and engage meaningfully with the world of ideas. Decision-making is a fundamental cognitive process that permeates nearly every aspect of human life, from the mundane choices of daily routines to the complex deliberations inherent in professional, ethical, and strategic contexts. For a well-educated audience, it is imperative to understand not only the mechanics of decision-making, but also the underlying psychological, neurological, and philosophical dimension that inform and shape our choices. At its core, decision-making involves selecting a course of action among multiple alternatives based on preferences, values, and available information. The process is typically framed within normative, descriptive, and prescriptive models. Normative decision theory, rooted in economics and logic, prescribes how decisions should be made to maximize utility. This model assumes rational agents with full access to information and unlimited cognitive processing abilities, a notion which, though elegant in theory, rarely holds true in practice. Descriptive decision theory, conversely, seeks to capture how decisions are actually made, incorporating the limitations and heuristics of human cognition. Prescriptive approaches aim to bridge the gap, offering tools and frameworks to improve decision outcomes under real-world constraints. Central to the descriptive understanding of decision-making is the dual process theory of cognition, which posits the existence of two systems. System 1, which is fast, intuitive, and analytical, and analyticative, and analytical. These systems interact dynamically, with System 1 often generating quick judgments that System 2 may endorse, override, or refine. For instance, a physician may intuitively diagnose a condition based on a patient's symptoms, System 1, then consult diagnostic tests and literature to confirm or revise that judgment, System 2. This dual system interplay underscores the importance of metacognition, our awareness and regulation of our own thought processes in making more reasoned and less biased decisions. Cognitive biases such as confirmation bias, availability, heuristic, and anchoring systematically steer our decision-making. For example, people tend to give more weight to information that confirms their pre-existing beliefs, or that comes readily to mind, even if it is statistically irrelevant. Recognizing these biases is the first step toward mitigating their influence, but it requires intentional practice and often external checks, such as peer review or algorithmic decision aids. From a neurological standpoint, decision-making involves a complex network of brain regions, particularly the prefrontal cortex, which is associated with executive functions like planning, reasoning, and impulse control. The orbitofrontal cortex plays a key role in evaluating rewards and punishments, while the amygdala contributes emotional balance, especially in risk-laden decision. Neuroeconomic studies using fMRI have illuminated how different brain areas are activated under various decision scenarios, suggesting that our brains integrate cognitive and affective data streams in a sophisticated evaluation process. This integration is not static. It evolves with experience, learning, and context. For instance, repeated exposure to decision tasks involving risk can lead to neural adaptation, affecting future risk assessment. Moreover, individual differences in neural architecture and neurotransmitter functioning can partially explain why some people are more risk-averse or impulsive than others. The context in which decisions are made significantly influences their quality and outcome. In organizational settings, decision-making often occurs in group contexts, where phenomena such as groupthink, polarization, and diffusion of responsibility can either hinder or enhance outcome. Groupthink, characterized by a desire for consensus that overrides critical evaluation, can lead to poor decisions, as famously exemplified by the Bay of Pigs invasion. To counter such dynamics, strategies like structured dissent, devil's advocacy, and anonymous input mechanisms have been employed to preserve the diversity of viewpoints and critical scrutiny. In contrast, collaborative decision-making frameworks, when well managed, can leverage collective intelligence, drawing on the varied experiences and perspectives of group members to arrive at more robust conclusions. Decision quality also hinges on the framing of choices. Behavioral economists have shown that the way options are presented gains V's, losses absolute V's. Relative terms can drastically alter preferences even when the underlying information remains constant. This phenomenon, known as the framing effect, illustrates the malleability of human preferences and the importance of transparent, consistent communication in decision environments. Ethical decision-making presents an especially nuanced challenge, as it often involves competing values, moral dilemmas, and uncertain outcomes. Traditional ethical frameworks, such as deontology, consequentialism, and virtue ethics, offer different lenses through which to evaluate choices. Deontology focuses on adherence to rules and duties, consequentialism on the outcomes of action, and virtue ethics on the character of the decision-maker. In practice, ethical decision-making often requires a synthesis of these perspectives, alongside contextual sensitivity and stakeholder analysis. For instance, a medical professional deciding whether to override a patient's autonomy for their own good must weigh respect for autonomy, deontological principle, against potential harm or benefit, consequentialist reasoning, and their own integrity and compassion, virtue ethics. Such decisions are rarely clear, cut, and benefit from structured frameworks like the 4 principles of biomedical ethics: autonomy, beneficence, non-maleficence, and justice, which provide a balanced, principled approach to ethical deliberation. Technological advancements have increasingly shaped how decisions are made, especially through data analytics and artificial intelligence. Algorithmic decision systems can process vast amounts of data to identify patterns and predict outcomes, offering unprecedented support in areas such as healthcare, finance, and logistics. However, these systems also introduce challenges related to transparency, accountability, and bias. Algorithms trained on biased data can perpetuate or even amplify existing inequalities, a concern that has spurred the development of ethical AU frameworks and calls for human-in-the-loop design. Moreover, reliance on algorithmic outputs can lead to automation bias, where human decision-makers unduly defer to machine recommendation. Ensuring that technological aids augment rather than supplant human judgment requires ongoing vigilance, interdisciplinary collaboration, and a commitment to ethical principle. Finally, decision-making is not solely an intellectual endeavor. It is deeply influenced by emotion, identity, and social context. Emotions can both enhance and impair decision. Positive emotions may broaden cognitive resources and foster creativity, while negative emotions, like fear or anger, can narrow focus and heighten risk sensitivity. Emotional intelligence, the ability to perceive, understand, and manage emotions, thus plays a crucial role in adaptive decision-making. Identity factors, including cultural background, personal values, and social roles, shape what individuals perceive as salient, acceptable, or obligatory. Cross-cultural research has revealed substantial variation in decision styles, such as the preference for individual versus collective decision-making, or analytic versus holistic reasoning. These differences underscore the importance of cultural competence and reflexivity in globalized decision contexts. In sum, decision-making is a multidimensional phenomenon that spans rational analysis, emotional intuition, ethical reasoning, and social negotiation. Understanding its complexities requires an integrative perspective that draws on cognitive psychology, neuroscience, philosophy, organizational theory, and emerging technologies. For the educated mind, engaging with the science and art of decision-making is not only intellectually enriching, but also practically vital. It enhances personal efficacy, professional judgment, and civic responsibility in an increasingly complex world. The distinction and interplay between consciousness and awareness lie at the heart of philosophy of mind, neuroscience, and cognitive science, touching upon fundamental questions about the nature of subjective experience and the architecture of the mind. While often used interchangeably in colloquial contexts, these terms carry nuanced meanings that differentiate them in technical discourse. Understanding this difference and their complex interrelations helps unravel deeper layers of human cognition and identity, illuminating how we perceive, interpret, and respond to the world. Consciousness, in its most basic definition, refers to the state of being aware of and able to think about oneself and the environment. It is typically described as the subjective quality of experience, what philosopher Thomas Nagel famously referred to as what it is like to be a conscious being. Consciousness encompasses the totality of phenomenal experience, the sights one sees, the thoughts one contemplates, the pain one feels, and the emotions one undergoes. That this phenomenological richness presents a challenge, often termed the hard problem of consciousness by David Chalmers. It points out the difficulty in explaining how physical processes in the brain give rise to subjective experience. Awareness, by contrast, is more modular and potentially less loaded with metaphysical connotations. It can be described as the capacity to perceive, to attend, or to process information, whether or not that information enters the stream of conscious experience. Awareness can be pre-reflective or unconscious, such as the brain's automatic tracking of environmental stimuli that one might not consciously notice, like subtle shifts in temperature or background noise. Cognitive psychology often distinguishes between different levels of awareness. For instance, between focal attention, directed conscious awareness, and peripheral or subliminal awareness, where stimuli are detected and influence behavior without rising to the level of conscious recognition. Importantly, one can be aware without being fully conscious in the phenomenological sense. Consider patients with blind sight, a neurological condition in which damage to the primary visual cortex prevents conscious visual perception. Despite reporting blindness, these individuals can often correctly identify the location or movement of objects in their blind field with greater accuracy than chance. This suggests that certain forms of awareness persist even when consciousness appears absent. Inversely, in states like lucid dreaming or during deep meditative absorption, individuals report intense states of consciousness that are inwardly focused, even while being minimally aware of external stimuli. This dissociation points to an important conceptual framework in contemporary consciousness studies, the distinction between access consciousness and phenomenal consciousness, as articulated by philosopher Ned Block. Access consciousness refers to information in the mind that is accessible for verbal report, reasoning, and guiding behavior. Phenomenal consciousness, however, refers to the raw feel of experience, independent of whether it is used in cognitive processing. A person might experience a vivid sunset, phenomenal consciousness, but not consciously reflect on its aesthetic impact or describe it in words, access consciousness. Neuroscientific investigations offer additional granularity. Brain imaging studies suggest that consciousness is not localized to a single area, but emerges from dynamic interactions among neural networks, especially the frontoparietal network. Awareness, particularly attentional mechanisms, are heavily mediated by structures such as the thalamus and anterior cortex. Intriguingly, disruptions in specific regions can selectively impair one without entirely erasing the other. For instance, damage to the prefrontal cortex may reduce access consciousness while preserving rich phenomenal experience, whereas anesthetics or coma-inducing injuries can suspend phenomenal consciousness while maintaining residual brain activity indicative of basic sensory awareness. Philosophical traditions have also long grappled with the distinction. In Eastern philosophy, particularly in Advaita, Vedanta, and various Buddhist schools, there is a careful dissection of different layers of awareness and states of consciousness. For instance, in Yogacara Buddhism, the mind is seen as layered, with surface awareness representing sensory and discursive cognition, while a deeper storehouse consciousness, alaya, vajnana, holds latent impressions and karmic seeds. These traditions emphasize the trainability of awareness and the ability to refine consciousness through meditative practices, an idea that modern contemplative neuroscience is beginning to explore through studies on mindfulness and altered states. In psychology, theories like global workspace theory, GWOP, by Bernard Bias, posit that consciousness arises when information is globally broadcast across cognitive systems, enabling flexible responses, learning, and reportability. Awareness, in this model, is akin to the spotlight of attention, focusing cognitive resources on a subset of inputs which may or may not enter the conscious workspace, depending on their salience and novelty. Another prominent model, integrated information theory, developed by Giulio Tononi, proposes that consciousness correlates with the degree to which a system integrates information. While highly mathematical in formulation, it implies that awareness is necessary, but not sufficient for consciousness. An entity might process inputs awareness, but lack the integration needed to produce a unified conscious experience. This analytical parsing of consciousness and awareness carries immense implications for fields as varied as artificial intelligence, ethics, and medicine. In AI, for example, systems can exhibit sophisticated awareness, like behavior, object recognition, speech processing, or adaptive learning, without any indication of subjective experience. This provokes questions about the necessary and sufficient conditions for machine consciousness, and whether mimicking awareness is enough to ascribe agency or moral status. In clinical medicine, disorders of consciousness such as vegetative states, locked-in syndrome, or minimally conscious states demand careful assessment tools to differentiate awareness from consciousness, as misdiagnosis can profoundly affect care decisions and ethical judgment. Moreover, the growing field of psychedelic science presents a frontier where consciousness and awareness are actively modulated. Substances like psilocybin, ELVs, can radically alter the structure of conscious experience, enhancing some forms of awareness, g. interoception, emotional sensitivity, while disrupting ordinary perception and narrative self-awareness. These altered states offer windows into how flexible and multidimensional consciousness is, and how awareness can be decoupled, expanded, or transformed. Despite substantial progress, the ultimate nature of consciousness and its relationship to awareness remains elusive. Some propose that consciousness is a fundamental property of the universe, akin to space and time, a view known as panpsychism. Others maintain a more functionalist stance, arguing that consciousness is an emergent property of complex computation, and that awareness is its cognitive scaffolding. Still others entertain dual aspect or neutral monist theories, suggesting that both mind and matter arise from a more fundamental substrate. As empirical science continues to map the neural and cognitive correlates of awareness, and philosophical frameworks evolve to grapple with the first-person nature of consciousness, the dialogue between disciplines becomes increasingly essential. Both constructs, though often overlapping, serve different explanatory roles. Awareness helps chart the terrain of cognitive operations and perceptual fidelity, while consciousness anchors our understanding of what it means to be, to have an inner life, to reflect, to suffer, to enjoy. In sum, while awareness can be likened to the lens through which experience is focused, consciousness is the light that brings that experience into being. They are deeply entwined, yet not identical, and the exploration of their boundaries continues to challenge and enrich our understanding of mind and self. Computational models of cognition serve as the cornerstone for understanding how the human mind processes information, solves problems, learns, and adapts. These models attempt to formalize cognitive processes through mathematical and algorithmic systems, essentially treating the mind as an information processing entity. The premise is rooted in the belief that cognitive functions, such as memory, attention, perception, and language, can be systematically studied and simulated through computational means. By articulating cognition in terms of rules, structures, and data manipulations, researchers aim to dissect the intricacies of mental operations in ways that are precise, testable, and replicable. The historical trajectory of computational cognitive models is deeply intertwined with developments in artificial intelligence and cognitive psychology. The inception of this paradigm can be traced back to the 1950s, particularly with the advent of digital computers, which proved a viable platform to simulate aspects of human thinking. Pioneering work by figures such as Alan Newell and Herbert Simon introduced the idea that cognition could be described through symbolic processing. The general problem solver and subsequent developments illustrated that reasoning and decision-making could be formalized using rules and heuristics. This approach, termed the symbolic or classical model, conceptualizes cognition as the manipulation of abstract symbols according to explicit rules, a theory bearing strong resemblance to logical inference system. However, while symbolic models laid essential groundwork, they were often criticized for their limitations in dealing with real-world cognitive phenomena, particularly those involving ambiguity, learning, and perception. This criticism paved the way for the rise of connectionist models, particularly in the 1980s. These models, commonly represented by artificial neural networks, took inspiration from the architecture of the brain, rather than depending on predefined symbolic rules. Connectionist systems learn from experience by adjusting the weights of connections among simple processing units. This learning-based, distributed representation allowed connectionist models to excel in tasks such as pattern recognition, language modeling, and motor control, offering a more biologically plausible mechanism. A key advantage of connectionist models is their ability to generalize from limited data and exhibit robust performance, even with incomplete information. Yet their interpretability remains a challenge. Unlike symbolic models, where cognitive processes are transparent and traceable, neural networks often operate as black boxes, making it difficult to extract clear explanations for their outputs. This opacity has driven efforts to integrate the strengths of both symbolic and connectionist approaches, giving rise to hybrid models of cognition. Such models aim to harness the interpretability of symbolic systems with the adaptive capabilities of neural networks. For example, the ACT-R, adaptive control of thought, rational framework attempts to represent cognition as a mixture of declarative memory modules and procedural knowledge, operating within a cognitive architecture that emulates human performance across a wide array of tasks. Beyond these traditional paradigms, more recent developments have seen the infusion of probabilistic and Bayesian approaches into cognitive modeling. These models propose that cognition fundamentally operates under conditions of uncertainty and that the mind functions as a statistical inference engine. In this view, human reasoning and perception are understood as processes of probabilistically inferring the most likely causes of observed data. Bayesian models have been particularly influential in explaining perceptual processes, language comprehension, and decision-making, where individuals must constantly update their beliefs in light of new evidence. These models offer a normative framework grounded in statistical theory, often aligning closely with empirical data on human behavior. Another critical direction in computational modeling involves reinforcement learning, which captures how agents learn to act in environments based on reward signals. This approach has found resonance in both neuroscience and psychology, providing insights into how organisms adjust behavior based on experience. The integration of reinforcement learning principles into cognitive models has helped elucidate mechanisms underlying habit formation, motivation, and even psychiatric disorders where reward processing may be impaired. One of the central debates in computational cognitive science revolves around the level of abstraction at which cognition should be modeled. Some researchers advocate for high-level algorithmic models that describe the structure and function of cognitive processes, akin to software that runs on the hardware of the brain. Others argue for biologically grounded models that strive to replicate the neural and anatomical details of cognition. This tension reflects a broader philosophical divergence. Whether the mind should be understood more like a computer running software or as an emergent phenomenon of neural dynamics. Both perspectives offer valuable insights, and ongoing research often seeks a synthesis that bridges abstract cognitive theories with neural implementation. Importantly, computational models are not merely theoretical constructs. They are powerful tools for empirical investigation. By formalizing hypotheses about cognitive processes, models can generate precise predictions that can be tested through experiment. For instance, a model of memory retrieval can predict response times or error patterns in recall tasks, which can then be compared with observed data. This iterative loop between modeling and experimentation has significantly advanced our understanding of mental processes, leading to models that are increasingly predictive and mechanistically detailed. Moreover, computational models of cognition are finding growing applications in diverse fields such as education, human-computer interaction, robotics, and clinical psychology. In education, cognitive models inform intelligent tutoring systems that adapt to a learner's individual pace and style. In clinical settings, models of cognitive dysfunction provide insights into conditions such as ADHD, schizophrenia, and Alzheimer's disease, offering frameworks to understand symptom patterns and develop intervention. In robotics and AI, cognitive models guide the design of agents that can reason, plan, and learn in ways that mirror human intelligence, facilitating more natural and intuitive interaction. As the field evolves, one of the most promising frontiers is the use of large-scale cognitive simulations that integrate multiple modalities, such as vision, language, and motor control. In a unified framework, advances in computing power, data availability, and machine learning algorithms are making it increasingly feasible to build comprehensive models that reflect the richness of human cognition. These models are beginning to approximate human-level performance on complex tasks, suggesting that we are inching closer to a more holistic understanding of the mind. Despite the progress, significant challenges remain. Ensuring that models generalize across tasks and domains, explaining individual differences in cognition, and grounding abstract models in real-world contexts are all ongoing concerns. Moreover, as models become more complex, maintaining interpretability and theoretical coherence becomes more difficult. The future of computational models of cognition will likely depend on a delicate balance between abstraction and realism, simplicity and fidelity, and data. In essence, computational models of cognition represent our most concerted effort to reverse engineer the mind by transforming qualitative theories into quantitative frameworks. They allow us to simulate, test, and refine our understanding of how thought emerges from matter, whether through symbolic systems, neural networks, Bayesian inference, or hybrid architectures. These models continue to illuminate the pathways by which brains give rise to minds, a quest that lies at the heart of cognitive science and artificial intelligence AI. Cognitive rehabilitation is a specialized and evolving domain within the broader field of neuropsychology and rehabilitation medicine, designed to address cognitive deficits that arise from neurological injuries or diseases. These deficits may involve memory, attention, executive functioning, language, visuospatial abilities, or processing speed, depending on the nature and location of the brain insult. Typically, cognitive rehabilitation is prescribed for individuals recovering from traumatic brain injury, TBI, stroke, neurodegenerative conditions such as Alzheimer's disease, multiple sclerosis, psychiatric conditions. Its ultimate goal is to restore function to the greatest possible extent, or when restoration is not feasible, to equip individuals with strategies to compensate for their impairments and maintain independence in daily life. At its core, cognitive rehabilitation involves two major therapeutic approaches: restorative and compensatory. Restorative therapy is based on the principle of neuroplasticity, the brain's inherent capacity to reorganize and rewire itself in response to damage. Through repetitive and targeted exercises, individuals engage in tasks designed to retrain specific cognitive functions, encouraging synaptic growth and functional remapping. For example, computerized training programs might be used to strengthen working memory, or attentional control exercises may help re-establish sustained focus. The evidence for such interventions is mixed but promising in some populations, particularly those in the acute or subacute phases post-injury, when neuroplastic potential is at its peak. Compensatory strategies, on the other hand, do not attempt to repair the underlying cognitive impairment, but rather teach the individual to work around it. This might involve the use of external aids, such as digital reminders, planners, or alarm systems for memory deficits. Internal strategies can also be taught, such as mnemonic devices, chunking for memory enhancement, or self-monitoring techniques to address executive dysfunction. These interventions are typically more appropriate for those in the chronic phase of recovery, or with progressive neurodegenerative conditions, where full cognitive restoration is not expected, but functional autonomy can still be supported. The design of a cognitive rehabilitation program is ideally individualized and interdisciplinary, often involving neurologists, neuropsychologists, occupational therapists, speech, language pathologists, and sometimes social workers. A thorough cognitive assessment is typically the first step, employing standardized neuropsychological tests to delineate the patient's cognitive profile, identify areas of strength and weakness, and guide the therapeutic plan. Contextual factors, such as the person's educational background, vocational goals, social support network, and emotional well-being, must also be considered, as cognitive performance is deeply embedded within psychosocial and environmental contexts. There is growing appreciation for the role of metacognition, one's awareness and understanding of their own cognitive processes, in successful rehabilitation. Interventions that enhance metacognitive abilities can empower patients to self-monitor their limitations, recognize errors, and adjust their strategies accordingly. This metacognitive training can be crucial, especially for individuals with frontal lobe injuries, who may experience anosognosia, or lack of awareness of their deficits. A well-calibrated understanding of their own cognitive limits is often a predictor of real-world functional outcome. An emerging trend in cognitive rehabilitation is the integration of technology. Virtual reality, VR, serious gaming, and telerehabilitation platforms offer new avenues for delivering cognitive training in engaging and ecologically valid ways. Simulations, for instance, can mimic real-world environments, where patients practice navigating a grocery store, managing finances, or planning transportation. Such immersive settings improve the transfer of training gains to everyday life, a long-standing challenge in cognitive rehabilitation. Additionally, The scalability and remote accessibility of digital tools make them particularly valuable in underserved or rural populations, or for individuals with mobility restrictions. Cognitive rehabilitation is also influenced by the growing body of research on brain, behavior, relationships, and the mechanisms of learning. Principles from cognitive neuroscience are increasingly used to fine-tune intervention. For example, spaced repetition, interleaving of tasks, and errorless learning paradigms have shown promise in enhancing memory retention and task acquisition. Furthermore, recent advances in neuroimaging provide tools to monitor the treatment-related brain changes, offering biomarkers for treatment efficacy and paving the way for personalized therapeutic approaches. Despite its promise, cognitive rehabilitation remains a field marked by challenges and ongoing debate. One significant issue is the heterogeneity of patient presentations. No two brain injuries are alike, and cognitive deficits often interact in complex, dynamic ways. This variability makes it difficult to conduct large-scale, randomized controlled trials, the gold standard in evidence-based medicine, without losing individual nuance. As a result, much of the literature is characterized by small sample sizes and limited generalizability. However, systematic reviews and meta-analyses do suggest moderate effect sizes for targeted cognitive interventions, particularly in domains such as attention and memory. Another complication is the difficulty of measuring real-world outcomes. Improvements on standardized cognitive tests do not always translate into better daily functioning or quality of life. Therefore, cognitive rehabilitation must be embedded within broader frameworks of functional recovery, including occupational reintegration, community participation, and emotional adjustment. This holistic view acknowledges that cognitive health is not merely the sum of discrete abilities, but is intimately tied to motivation, mood, social support, and life purpose. The ethical dimension of cognitive rehabilitation also deserves mention. As the field increasingly adopts sophisticated technological tools and interventions informed by neuroscience, questions arise about accessibility and patient autonomy. High-tech interventions may be costly or limited to urban centers, potentially exacerbating disparity. Moreover, clinicians must balance hope with realism, especially in cases of degenerative diseases where cognitive decline is inevitable. The goal, in such cases, often shifts from recovery to adaptation, dignity, preservation, and maximizing quality of life. In recent years, cognitive rehabilitation has also begun to intersect with preventative neuroscience. Evidence suggests that cognitive reserve, a construct referring to the brain's resilience to damage, can be enhanced by lifelong engagement in intellectually stimulating activities, physical exercise, social interaction, and healthy diet. While not a form of rehabilitation per se, these lifestyle interventions can augment the brain's baseline capacity and buffer against cognitive decline. This preventative approach underscores the need for public health strategies that promote cognitive wellness across the lifespan, not just after injury or disease. In summary, cognitive rehabilitation represents a vital, complex, and a rapidly evolving frontier in the effort to support individuals facing cognitive impairment. Grounded in neuropsychology and enriched by technological and neuroscientific advancements, it offers both hope and practical pathways toward recovery and adaptation. While challenges in standardization, outcome measurement, and access persist, the field continues to refine its tools and expand its horizons, driven by the central humanistic goal of restoring agency, purpose, and dignity in the lives of those affected by cognitive loss. Cognitive neuroscience is a field at the intersection of psychology and biology, dedicated to understanding how the brain enables the mind. It seeks to uncover the biological underpinnings of cognitive functions, such as perception, memory, language, attention, and decision-making. By integrating insights from neuroscience, psychology, computer science, cognitive science, cognitive neuroscience aims to create a coherent model of how brain activity gives rise to mental processes. At its core, cognitive neuroscience addresses a fundamental question. How does neural activity translate into thought and behavior? To tackle this, researchers employ a variety of methodological approaches, including neuroimaging techniques like functional magnetic resonance imaging, fMRI, electroencephalography, magnetoidal-magnetic stimulation, Each of these tools provides a different window into the functioning brain. For example, MRI measures blood flow changes that correlate with neuronal activity, allowing researchers to observe which brain areas are involved in specific tasks. EEG and MEG, on the other hand, offer excellent temporal resolution, capturing electrical and magnetic signals that occur on the order of milliseconds, thus giving insight into the timing of cognitive processes. One of the major achievements of cognitive neuroscience has been mapping the localization of cognitive functions within specific brain regions. For example, the prefrontal cortex is crucial for executive functions such as planning, decision-making, and inhibitory control. The hippocampus, located in the medial temporal lobe, is central to the formation of new episodic memory. The occipital lobe, particularly the primary visual cortex, is responsible for processing visual information, while the parietal cortex plays a significant role in spatial awareness and attention. Language processing has also been extensively studied, with Broca's area implicated in speech production and Wernicke's area in comprehension. Beyond localizing function, cognitive neuroscience explores how different regions interact in networks. The brain is not merely a collection of isolated modules, but a highly interconnected system where complex behaviors emerge from dynamic interactions among distributed networks. For instance, the default mode network, DEM, active during rest and internal thought, contrasts with the task positive network that engages during goal-directed activity. Understanding the interplay between such networks has deepened our knowledge of mental health and disease. Disruptions in network connectivity have been linked to disorders like schizophrenia, depression, and autism spectrum conditions. Another critical area of study within cognitive neuroscience is the investigation of consciousness and self-awareness. Though elusive, consciousness is gradually being unpacked using empirical approaches. Theories like the global workspace theory and integrated information theory propose mechanisms by which conscious awareness might arise from neural processes. Researchers examine phenomena such as visual awareness, attention, and the neural correlates of subjective experience to gain insights into the neural basis of consciousness. While consensus remains out of reach, progress in this area continues to challenge and refine our understanding of what it means to be aware. Cognitive neuroscience also benefits from computational modeling. By simulating neural processes through algorithms and artificial neural networks, scientists can test hypotheses about cognition in silico before applying them to the biological system. The rise of machine learning and deep learning has further enabled the development of models that mimic human learning, object recognition, and language processing. These computational tools not only enhance our understanding of brain function, but also contribute to the development of brain-inspired artificial intelligence systems. Importantly, cognitive neuroscience does not operate in a vacuum. It informs and is informed by clinical neuroscience. For example, studies of patients with brain lesions, such as those caused by stroke or neurodegenerative diseases, provide invaluable insights into the brain-behavior relationship. The famous case of a patient who had his medial temporal lobes removed to treat epilepsy revealed the critical role of the hippocampus in memory consolidation. Similarly, understanding the neural mechanisms of disorders like Alzheimer's disease, Parkinson's disease, and multiple sclerosis has been advanced through cognitive neuroscience methods, leading to better developmental cognitive neuroscience is a growing subfield that examines how cognitive functions emerge and change over the lifespan. From infancy to old age, the brain undergoes substantial structural and functional changes. By studying these developmental trajectories, researchers can identify sensitive periods for learning, the impact of early experiences, and how aging affects cognitive capacity. Such research has practical implications for education, child development, and interventions aimed at mitigating cognitive decline. The field also addresses individual differences in cognition. Why do some people excel at multitasking, while others have exceptional memory or heightened emotional sensitivity? Cognitive neuroscience investigates the genetic, environmental, and neurobiological factors that contribute to these differences. Twin studies help parse out heritable components, while neuroimaging allows researchers to correlate brain structure and activity with performance on cognitive tasks. Ethical considerations are increasingly relevant in cognitive neuroscience, especially as techniques become more powerful and invasive. Issues related to neuroprivacy, cognitive enhancement, and potential misuse of neuroscientific findings in legal or commercial contexts demand careful scrutiny. As we gain the ability to decode mental states or potentially alter them, the responsibility to use such knowledge wisely grows in tandem. Cognitive neuroscience is also deeply intertwined with philosophy. Questions that were once the purview of metaphysics, such as the nature of free will, the mind-body problem, and the essence of subjective experience, are now being tackled with empirical tools. While neuroscience may never fully explain the qualia or intrinsic feel of experiences, it offers a framework for understanding the physical basis of such phenomena. Education and public policy are other domains influenced by cognitive neuroscience. Insights into attention, learning, and memory have led to evidence-based teaching strategies. Understanding how stress and emotion affect cognition informs workplace design and mental health initiatives. By grounding policies in neuroscientific evidence, societies can make more informed decisions about everything from juvenile justice to elder care. Despite its many advances, cognitive neuroscience faces several challenges. The complexity of the brain means that findings are often correlational rather than causal. While techniques like TEMS and lesion studies offer some causal inference, many questions remain unanswered. Replicability, methodological variability, and interpretation of large-scale data also pose hurdles. Nonetheless, the interdisciplinary nature of cognitive neuroscience ensures continuous methodological innovation and theoretical refinement. In essence, cognitive neuroscience provides a window into the most complex organ in the known universe, the human brain. By elucidating the biological basis of thought, emotion, and behavior, it bridges the gap between neurons and cognition, biology, and experience. As technologies advance and theoretical frameworks evolve, cognitive neuroscience holds the promise of deeper understanding and practical applications that touch every aspect of human life, from health and education to ethics and artificial intelligence. Cognitive load is a foundational concept in educational psychology that explores how the human brain processes and retains new information, particularly within instructional contexts. First developed by John Sweller in the late 1980s, COLT is grounded in an understanding of the human cognitive architecture, especially the limitations of working memory and the mechanisms by which information is transferred to long-term memory. At its core, COLT posits that effective learning occurs when instructional design aligns with our cognitive system's capabilities, particularly by managing the load imposed on working memory during learning activities. This theory has significant implications for designing educational materials and teaching strategy, particularly in fields that require the acquisition of complex or voluminous information, such as mathematics, science, and technical subjects. Working memory is notoriously limited in both capacity and duration. Typically, it can hold around 7 elements, give or take 2, at any given moment, and these elements fade rapidly unless actively maintained or encoded into long-term memory. In contrast, long-term memory is vast and durable, storing knowledge as interconnected schemas, organized patterns of thought or behavior that help us interpret and respond to new situations. Learning, in essence, involves constructing and refining these schemas. When learners are presented with new information, they must process it in working memory before it can be integrated into long-term memory. However, if the cognitive load, the mental effort required to process this information, exceeds the working memory's capacity, learning is hindered. COLT categorizes cognitive load into 3 types: intrinsic, extraneous, and germane. Intrinsic load refers to the inherent difficulty of the material itself, which is determined by the complexity of the content and the learner's prior knowledge. For instance, learning to solve a basic algebraic equation may impose low intrinsic load on an experienced mathematician, but could be quite taxing for a novice. Extraneous load, by contrast, is not essential to the learning task, but results from the way information is presented. Poorly designed instructional materials, such as cluttered slides, irrelevant animations, or overly complex language, can unnecessarily burden the learner's cognitive resources. Minimizing extraneous load is a primary goal in an instructional design because it allows learners to allocate more of their cognitive resources to processing the core material. Germane load, the third type, represents the mental effort devoted to schema construction and automation. Unlike extraneous load, germane load is beneficial to learning. Instruction should aim not only to reduce extraneous load, but also to foster germane load by encouraging learners to engage actively with the material through strategies like elaboration, self-explanation. An important implication of CULP is the concept of expertise reversal. As learners gain more knowledge, instructional techniques that were once helpful can become redundant or even detrimental. For example, worked examples, fully solved problems provided for study, are highly effective for novices because they reduce extraneous load and support schema acquisition. However, for advanced learners, these examples may become unnecessary or interfere with the application of their existing schemas, leading to increased cognitive load. Thus, instruction must be adaptive, evolving with the learner's level of expertise. Another key strategy arising from CULP is the segmentation principle, which suggests that breaking information into manageable chunks can facilitate learning. This principle is especially relevant in multimedia learning environments, where videos or interactive modules can easily overwhelm learners if not carefully structured. By controlling the pacing and sequencing of information, educators can help learners process complex material more effectively. Also informs the modality effect, which emphasizes the benefits of distributing cognitive load across different sensory channels. For instance, combining visual and auditory inputs, such as using spoken narration alongside diagrams, can enhance learning by reducing the burden on any single channel. However, this benefit only holds when the modalities complement rather than compete with each other. Presenting redundant information in both text and speech can actually increase extraneous load and hinder learning, a phenomenon known as the redundancy effect. Moreover, the split attention effect warns against presenting multiple sources of information that learners must integrate themselves, such as a diagram on one page and its explanation on another. Integration of related elements into a cohesive whole is essential to avoid unnecessary cognitive effort. In practical terms, the application of CULP has transformed the design of textbooks, e-learning platforms, and classroom instruction. Teachers are encouraged to scaffold learning by introducing new concepts gradually, connecting them to prior knowledge, and avoiding cognitive overload. For instance, in science education, students might first observe a phenomenon, then study a simplified model, and finally explore the underlying mechanism through guided inquiry. Similarly, digital platforms use CULP principles to structure content into interactive lessons that adapt to the learner's progress. Beyond formal education, CULP has implications for training in professional settings, such as aviation, medicine, and military operations, where complex procedures must be learned and performed under pressure. In these contexts, simulation-based training and decision Support systems are often designed to align with cognitive load principles, ensuring that essential information is accessible without overwhelming the user. Critics of QOLT have raised concerns about its empirical basis and generalizability. Some argue that cognitive load is difficult to measure objectively, and that distinctions between types of load may blur in practice. Additionally, individual differences in working memory capacity, motivation, and prior knowledge can influence how cognitive load is experienced and managed, suggesting a need for more personalized instructional approaches. Nevertheless, the theory continues to evolve, incorporating insights from neuroscience, instructional technology, and educational research. Recent developments include the use of physiological indicators, such as eye tracking and pupillometry, to assess cognitive load in real time, offering more precise data to inform instructional design. In conclusion, cognitive load theory provides a robust framework for understanding how people learn and how instruction can be optimized to support that process. By recognizing the limitations of working memory and the role of schema construction in long-term learning, QOLT guides educators in designing materials and activities that are both cognitively efficient and pedagogically effective. As learning environments become increasingly complex and technologically mediated, the principles of QOLT will remain essential for ensuring that educational experiences are not just informative, but truly transformative. Cognitive ergonomics is a vital subfield of ergonomics that focuses on understanding how cognitive processes, such as perception, memory, reasoning, and motor response, interact with elements of human-made system. It deals with the mental workload, decision-making, human reliability, work stress, and training as these factors affect the efficiency, safety, and effectiveness of systems involving human interaction. While traditional ergonomics is often associated with physical considerations such as posture and repetitive strain injuries, cognitive ergonomics steps into the realm of the mind, concerned with how individuals process information in dynamic, often complex environments. This is especially pertinent in high-stakes domains such as aviation, healthcare, nuclear power, and increasingly in digital interfaces and artificial intelligence systems. The origins of cognitive ergonomics trace back to World War, i.e., a period that demanded optimized human-machine interaction under stressful and error-intolerant conditions. Failures in interpreting cockpit gauges or misjudgments in command centers revealed the inadequacy of purely physical ergonomic design. Researchers began studying how people perceive, understand, and react to information, ultimately shaping the cognitive systems design approach. Since then, the discipline has expanded, drawing from cognitive psychology, systems engineering, human-computer interaction, and neuroscience to create systems that not only accommodate human mental capabilities, but actively support and enhance them. One core focus of cognitive ergonomics is mental workload, a construct that describes the demand placed on a human cognitive system during a task. High mental workload can lead to fatigue, reduced attention, and increased error rates, while too little can lead to boredom and decreased vigilance. Cognitive ergonomics seeks to find the optimal workload, what is sometimes referred to as the Goldilocks zone, where individuals remain engaged and perform efficiently. This is assessed through both objective measures, such as task performance, and physiological indicators, e.g. heart rate variability, and subjective scales like the NASA Task Load Index. Designers use these insights to shape systems that balance demands and capabilities, often by simplifying interfaces, automating routine processes, or providing adaptive support. Another fundamental aspect is decision-making under uncertainty. In real-world tasks, such as piloting an aircraft, managing a control room, or performing surgery, operators must make decisions based on incomplete, ambiguous, or rapidly changing information. Cognitive ergonomics analyzes the heuristics and biases that influence such decision-making processes. For example, the availability heuristic may lead a radiologist to overdiagnose a condition they recently encountered, while confirmation bias can skew an air traffic controller's interpretation of incoming data. Understanding these cognitive pitfalls enables system designers to create decision aids, such as diagnostic checklists, decision trees, or real-time analytics, that guide users toward more rational outcomes. Closely related is the concept of situation awareness, which refers to an individual's perception of environmental elements, comprehension of their meaning, and projection of their status into the near future. Poor situation awareness is a frequent contributor to accidents and errors, particularly in domains like aviation, maritime operations, and emergency response. Cognitive ergonomics contributes by designing interfaces that present critical information clearly and contextually, minimizing the cognitive effort required to maintain situational awareness. Head-up displays, color-coded alerts, and spatial data visualization are examples of such cognitive design tools. Human-computer interaction, CC, has emerged as a particularly fertile ground for applying cognitive ergonomic principles. As society becomes increasingly digital, the number and complexity of human interactions with software systems have grown exponentially. Poorly designed software can result in user frustration, errors, and inefficiency, not due to user incompetence, but due to cognitive mismatches between human expectations and system logic. Cognitive ergonomics informs the design of intuitive user interfaces, efficient workflows, and meaningful feedback mechanisms. It ensures that users do not become human error statistics, but are empowered as active participants in an intelligent system. Automation is another domain where cognitive ergonomics plays a crucial role, particularly in evaluating the shifting boundaries of responsibility between human and machine. While automation can reduce human workload, it can also result in skill degradation, reduced vigilance, and the out-of-the-loop performance problem. These issues become critical in scenarios requiring human intervention during system failure. For instance, pilots in highly automated cockpits may struggle to reorient themselves during a system anomaly, having been passive observers for extended periods. Cognitive ergonomics offers frameworks for designing automation that keeps humans engaged and informed, promoting joint human-machine cognition rather than outright replacement. Training and skill acquisition also fall within the purview of cognitive ergonomics. In designing training programs, it is essential to consider how people learn, retain, and transfer knowledge to real-world setting. Concepts like cognitive load theory guide the structuring of instructional materials to avoid overwhelming the learner. Simulators, scenario-based learning, and adaptive e-learning systems are designed with these principles in mind to accelerate expertise without incurring cognitive strain. Moreover, with the rise of virtual and augmented reality tools, cognitive ergonomics ensures these technologies are not only immersive, but cognitively congruent with real-world demands. Work stress and fatigue, although often considered psychological or organizational issues, are intrinsically linked to cognitive functioning. High stress can impair attention, memory, and executive function, leading to higher error rates and degraded performance. Ergonomists assess and redesign work environments, mitigate cognitive stresses, often by adjusting shift patterns, improving lighting and acoustics, or providing better task structuring. In critical systems, fatigue risk management systems are now informed by cognitive science to predict and prevent performance lapses. Importantly, the field is increasingly intersecting with neuroscience, offering biological insights into how the brain manages cognitive tasks. Functional memory and studies reveal the neural correlates of attention, multitasking, and decision-making. Such data are beginning to inform ergonomic design directly, enabling a more personalized, neuroadaptive approach to system configuration. For instance, real-time brain monitoring could one day allow workstations to adjust complexity based on the operator's cognitive state. Cognitive ergonomics is not merely about avoiding errors. It is about optimizing human potential in complex environments. As technology continues to evolve through i.e. wearable devices and smart environments, cognitive ergonomics ensures that these advancements remain human-centered. The goal is not to make humans fit the system, but to design systems that fit human cognition. This principle is not only a matter of usability or safety, it is fundamentally about dignity, empowerment, and trust in human capability. The future of cognitive ergonomics lies in hybrid systems where human insight and machine intelligence coalesce. In these systems, understanding the limits and strengths of human cognition will be as important as technical innovation, whether in personalized healthcare dashboards, intelligent tutoring systems, or decision support tools in space missions. Cognitive ergonomics ensures that human cognition remains at the core of technological progress. Its influence extends beyond ergonomics into ethics, policy, and design, advocating for a future where humans and systems not only coexist, but enhance one another in meaningful, measurable ways. Cognitive dissonance is a foundational concept in psychology, introduced by Leon Festinger in 1957, which describes the mental discomfort experienced when an individual holds two or more contradictory beliefs, values, or attitudes simultaneously, or when their behavior conflicts with their beliefs. This discomfort acts as a psychological tension that people are motivated to reduce, often by changing their attitudes, beliefs, or actions. Although seemingly straightforward, cognitive dissonance has profound implications for understanding human motivation, decision-making, and the consistency of our self-concept. At its core, cognitive dissonance stems from the drive for internal psychological consistency. Humans have a deep-rooted desire to perceive themselves as rational and coherent. When confronted with information or behaviors that challenge this self-perception, discomfort arises. This discomfort is not merely theoretical or abstract. It can manifest physiologically through increased heart rate, perspiration, or measurable changes in brain activity, particularly in areas associated with emotional conflict, such as the anterior cortex. To illustrate cognitive dissonance, consider a common example: a smoker who knows that smoking is harmful to their health. This individual experiences dissonance between their behavior, smoking, and their belief that smoking is dangerous. To reduce this dissonance, the smoker might rationalize their habit by downplaying the health risks. My grandfather smoked and lived to 90, questioning the validity of the research. The studies are inconclusive, or altering their behavior by quitting smoking. Each of these responses serves to restore psychological equilibrium, though only the latter aligns behavior with the initial belief. Cognitive dissonance does not occur in a vacuum. It is context, sensitive and influenced by factors such as the importance of the conflicting beliefs, the degree of discrepancy, and the individual's perceived agency over the situation. The greater the importance and perceived inconsistency, the stronger the dissonance. For instance, when individuals make significant decisions, such as purchasing a car or choosing a political candidate, they often engage in post-decision dissonance reduction, a process where they amplify the positive attributes of the chosen option and devalue the rejected alternative. This spreading of alternatives helps to reinforce the validity of their choice and minimize regret. Interestingly, cognitive dissonance plays a critical role in attitude change, often more effectively than external persuasion. Festinger and Carl Smith's seminal 1959 experiment demonstrated this elegantly. In the study, participants performed a dull task and were then asked to tell another person that it was enjoyable. Some were paid $1, others $20. Paradoxically, those paid only $1 reported enjoying the task more. The explanation lies in dissonance. Those paid $1 lacked sufficient external justification for lying, so they resolved the inconsistency by altering their internal attitude toward the task. In contrast, the $20 group had ample external justification, and thus experienced less dissonance. The implications of cognitive dissonance theory extend across diverse domains, including education, marketing, politics, and ethics. In education, students often confront information that challenges pre-existing beliefs. Encouraging critical thinking through dissonance-inducing strategies, such as exposing contradictions in their reasoning, can promote deeper learning and conceptual change. In marketing, dissonance is strategically harnessed to increase customer commitment. For example, after a purchase, companies may send confirmation messages or positive testimonials to reassure consumers and reduce potential buyers' remorse. In politics, dissonance frequently shapes ideological entrenchment. When confronted with information that contradicts their political identity, individuals often engage in motivated reasoning, selectively accepting supportive evidence and dismissing contradictory data to reduce dissonance. This phenomenon contributes to polarization, as people insulate themselves from conflicting viewpoints to maintain a coherent worldview. Moreover, cognitive dissonance has ethical dimensions, particularly in justifying immoral action. Soldiers, for instance, may dehumanize enemy combatants or adopt moral disengagement strategies to reconcile their actions with internal moral standards. Neuroscientific research has begun to uncover the underlying mechanisms of cognitive dissonance. Functional MRI studies have shown that the experience of dissonance activates brain regions associated with conflict monitoring and emotional distress. Moreover, the resolution of dissonance through attitude, change, or justification engages reward pathways, suggesting a neurobiological basis for the motivation to reduce inconsistency. These findings support the notion that cognitive dissonance is not merely a social construct, but an evolutionarily ingrained mechanism for adaptive decision-making and self-regulation. Beyond individual psychology, cognitive dissonance can influence collective behavior and cultural dynamics. Societies often develop shared narratives and belief systems to maintain collective coherence. When cultural or religious doctrines are challenged, either through scientific discoveries or social change, dissonance arises at a group level. Reactions can range from reinterpretation and reform to outright denial and backlash. The cultural evolution of norms around issues like gender equality, climate change, or vaccination can be viewed in part through the lens of collective dissonance reduction. Critics of the theory argue that cognitive dissonance may not be the only explanation for behavior change or inconsistency. Alternative models, such as self-perception theory, proposed by Daryl Bem, suggest that individuals infer their attitudes from observing their own behavior, particularly in the absence of strong pre-existing belief. However, the weight of empirical evidence generally favors dissonance theory, especially in situations involving significant moral, emotional, or identity-laden conflict. Importantly, the two theories are not necessarily mutually exclusive. Self-perception may explain attitude formation in low-stakes contexts, while cognitive dissonance accounts for deeper internal conflicts. Cognitive dissonance is also closely linked to the concept of self-justification, a process by which individuals defend and rationalize their actions to preserve their self-concept. This can lead to escalation of commitment, where people continue investing in failed endeavors to avoid admitting a mistake. Recognizing this tendency has practical applications in therapy, conflict resolution, and leadership. Therapists may help clients identify and resolve internal dissonances, contributing to psychological distress. Mediators may use dissonance to nudge parties toward reconciliation. Leaders who acknowledge dissonance transparently, especially during crises, can foster trust and adaptive change. In sum, cognitive dissonance is a powerful, pervasive force in human psychology, shaping how we think, feel, and act. It serves as a regulatory mechanism that prompts us to seek consistency, make sense of the world, and preserve our identity. While this drive for coherence can promote growth and change, it can also entrench irrational beliefs and resistance to evidence. Understanding and harnessing cognitive dissonance, both in ourselves and in others, can enhance critical thinking, empathy, and decision-making in an increasingly complex and polarized world. Cognitive development refers to the progressive and dynamic growth of an individual's ability to think, reason, understand, and remember, encompassing a broad range of mental processes that form the foundation of learning and adaptation. This complex process begins in infancy and continues throughout the lifespan, though the most rapid and significant changes occur in childhood and adolescence. Rooted in both biological maturation and environmental experience, cognitive development is shaped through interactions between genetic predispositions and social, cultural, and educational influences. Central to the study of cognitive development are several theoretical frameworks, most notably those proposed by Jean Piaget, Lev Vygotsky, and more contemporary cognitive scientists who have expanded upon or challenged ideas. Jean Piaget's theory remains one of the most influential in understanding cognitive development, emphasizing that children move through a series of stages characterized by qualitatively different ways of thinking. According to Piaget, the stages sensorimotor, preoperational, concrete operational, and formal operational represent a natural sequence of cognitive maturation. In the sensorimotor stage, from birth to about 2 years, infants learn through direct sensory and motor interactions with the environment. They gradually develop object permanence and begin to understand that objects continue to exist even when not visible. In the preoperational stage, roughly ages 2 to 7, children start using language and symbolic thinking, but struggle with logic and understanding the perspectives of others, a phenomenon known as egocentrism. The concrete operational stage, from 7 to 11 years, marks the development of logical thinking about concrete objects and events, though abstract reasoning remains limited. Finally, in the formal operational stage, beginning around age 12, individuals develop the capacity for abstract, hypothetical, and deductive reasoning, which allows them to think about possibilities and systematically solve problems. While Piaget highlighted the importance of stages and intrinsic developmental processes, Lev Vygotsky offered a complementary perspective that emphasized the role of social interaction and cultural context in cognitive development. Vygotsky introduced the concept of the zone of proximal development, ZEPT, which refers to the range of tasks that a child cannot yet perform independently, but can accomplish with guidance and support from a more knowledgeable other, such as a teacher or peer. This theory underscores the importance of scaffolding, structured support that is gradually removed as the learner becomes more competent. Unlike Piaget, who believed that development precedes learning, Vygotsky argued that learning leads development and that cognitive growth is largely mediated by language, culture, and interpersonal communication. His emphasis on the socio-cultural dimension of cognitive development has had profound implications for educational practices, advocating for interactive, collaborative, and contextually relevant learning experiences. In addition to these classical theories, modern cognitive science and developmental psychology have expanded the understanding of cognitive development by incorporating insights from neuroscience, information processing theories, and dynamic systems approaches. Neuroscientific research has illuminated the biological underpinnings of cognitive development, revealing how brain structures and neural connectivity evolve during childhood and adolescence. The prefrontal cortex, crucial for executive functions such as planning, attention, and problem solving, undergoes significant maturation during adolescence, which corresponds to improved cognitive control and decision-making abilities. Moreover, advancements in neuroimaging have demonstrated that cognitive development is not a linear process, but involves complex, interrelated changes across multiple brain regions and systems. Information processing theories offer another valuable perspective, likening the mind to a computer that encodes, stores, and retrieves information. These theories focus on how children develop increasingly sophisticated strategies for processing information, such as improved memory capacity, faster processing speed, and more effective use of metacognitive strategies, thinking about one's own thinking. This approach has been instrumental in explaining individual differences in cognitive abilities and the mechanisms through which cognitive skills are acquired and refined over time. For instance, research has shown that working memory capacity and attentional control are strong predictors of academic achievement and are susceptible to training and intervention. Another important aspect of cognitive development is the role of language, not only as a tool for communication, but as a medium for thought itself. Language facilitates abstract reasoning, categorization, and the internalization of cultural norms and knowledge. Bilingualism, for example, has been associated with enhanced cognitive flexibility and executive function, illustrating how diverse linguistic environments can shape cognitive outcomes. Furthermore, emotional and social development are intricately linked to cognitive development. Emotional regulation, theory of mind, the ability to attribute mental states to oneself and others, and empathy all require complex cognitive operations and develop in tandem with broader cognitive capacities. Environmental factors, including parenting style, educational quality, socioeconomic status, and exposure to stress or trauma, significantly influence cognitive development. Enriched environments that provide ample opportunities for exploration, problem-solving, and social interaction tend to foster more robust cognitive growth. Conversely, adverse conditions such as poverty, neglect, and chronic stress can hinder cognitive development, particularly during critical periods when the brain is most plastic. Interventions aimed at early childhood education and family support have demonstrated substantial benefits in mitigating these negative effects and promoting equitable cognitive outcomes. Moreover, cognitive development does not cease in childhood, but continues into adulthood, albeit at a slower pace and with greater individual variability. Lifelong learning, neuroplasticity, and cognitive reserve, the brain's resilience to aging and pathology, highlight the dynamic nature of cognition across the lifespan. Aging is typically associated with declines in certain cognitive functions, such as processing speed and working memory, but other areas, like vocabulary and accumulated knowledge, often remain stable or even improve. Cognitive engagement through intellectual, social, and physical activities has been shown to buffer against age-related decline and enhance quality of life. In sum, cognitive development is a multifaceted, lifelong process shaped by an interplay of biological, psychological, factor. From the foundational theories of Piaget and Vygotsky to contemporary insights from neuroscience and information processing, the study of cognitive development reveals the extraordinary complexity of the human mind. Understanding this development not only enriches our knowledge of how individuals grow and learn, but also informs educational practices, parenting strategies, and social policies aimed at supporting optimal cognitive outcomes for all individuals. Cognitive control, often referred to as executive function, represents a set of mental skills that enable individuals to regulate their thoughts and actions in accordance with internal goals. Among its core components, inhibition plays a foundational role. Inhibition allows the brain to suppress irrelevant or inappropriate responses, impulses, and distractions in order to engage in goal-directed behavior. This interplay between cognitive control and inhibition underlies a broad range of human activities, from resisting temptations to solving complex problems or navigating social interactions. Understanding these functions not only sheds light on how the brain orchestrates behavior, but also provides insight into various psychiatric and neurological disorders where these processes break down. And at the heart of cognitive control lies the prefrontal cortex, PC, a brain region evolutionarily developed in humans and primates that orchestrates high-level cognitive processes. The PC does not operate in isolation, but interacts dynamically with subcortical structures like the basal ganglia and thalamus. These circuits allow for the flexible updating of working memory, the shifting of attention, and crucially, the inhibition of prepotent or automatic responses. The ability to override these automatic responses is particularly important when habitual behavior is maladaptive or when one must engage in novel problem-solving tasks. When inhibition, in particular, is not a monolithic construct. It comprises multiple forms, including response, inhibition, interference, control, and cognitive inhibition. Response inhibition refers to the capacity to suppress motor action. For example, stopping oneself from blurting out an inappropriate comment. This form of inhibition is commonly tested using tasks like the go-no, Google, or stop signal tasks. Interference control involves resisting distractions and ignoring competing stimuli, while cognitive inhibition deals with the suppression of irrelevant memories or thoughts, as observed in directed forgetting paradigms. These distinct yet interrelated domains illustrate the multifaceted nature of inhibitory processes. Neuroimaging and electrophysiological studies have illuminated how these inhibitory mechanisms manifest in the brain. For instance, during tasks requiring response inhibition, increased activation is typically observed in the right inferior frontal gyrus, anterior cingulate cortex, acute and supplementary motor area. These regions are thought to signal conflict and exert top-down control to halt inappropriate motor plans. The subthalamic nucleus, then, part of the basal ganglia, also plays a pivotal role in rapid inhibitory control, acting as a brake when a stop signal is perceived. This inhibitory circuit allows the brain to swiftly adjust behavior in response to changing environmental demands. Beyond experimental paradigms, cognitive control and inhibition are essential for everyday functioning. Consider the example of driving. A driver must continuously inhibit distractions, e.g., cell phone notifications, suppress impulsive behavior, e.g., speeding through a yellow light, and adapt behavior based on traffic signals or unexpected pedestrian movement. These real-world tasks place heavy demands on inhibitory processes and highlight their adaptive value. Similarly, in academic or professional settings, the ability to inhibit distractions and maintain focus is crucial for sustained intellectual engagement. Developmentally, cognitive control and inhibition undergo substantial maturation from childhood into early adulthood. Young children often struggle with tasks requiring inhibitory control, which is reflected in behaviors like difficulty sharing, poor impulse control, and distractibility. These tendencies gradually diminish as the FFC matures, typically peaking in performance during the third decade of life. Importantly, individual differences in inhibitory capacity are predictive of long-term outcomes, such as academic success, emotional regulation, and even physical health. The famous marshmallow test exemplifies this, where children who exhibited greater delay of gratification showed more favorable life trajectories decades later. However, cognitive control and inhibition are also vulnerable to disruption. In neurodevelopmental disorders like attention deficit hyperactivity disorder, at H, impaired inhibition is a core feature contributing to impulsivity and attentional lapses. Similarly, in obsessive-compulsive disorder, OCT, the inability to suppress intrusive thoughts and repetitive behaviors reflects dysregulated inhibitory processes. These conditions often show altered activation in Fexy circuits and diminished connectivity between key control regions. In neurodegenerative diseases such as Parkinson's and Alzheimer's, declining cognitive control manifests as difficulty switching tasks, increased susceptibility to distraction, and impaired suppression of irrelevant memories. Furthermore, inhibition is sensitive to both internal and external modulators. Acute stress, fatigue, and alcohol intake are known to impair inhibitory control, leading to riskier decisions and lapses in judgment. Conversely, interventions such as mindfulness training, cognitive behavioral therapy, SEB, demonstrated efficacy in enhancing executive function, including inhibitory capabilities. These findings offer promising avenues for both clinical treatment and educational strategies aimed at strengthening cognitive control. One intriguing aspect of cognitive inhibition is its relationship with creativity and mental flexibility. While inhibition is often associated with constraint and self-regulation, an optimal level of inhibitory control appears essential for creative thought. Excessive inhibition may stifle novel idea generation, whereas deficient inhibition can lead to chaotic or disorganized thinking. This balance underscores the nuanced role of inhibition, not as a rigid suppressor, but as a dynamic gatekeeper that regulates the flow of thoughts and behaviors in accordance with situational demands. Another important dimension involves the conscious versus unconscious nature of inhibition. Some inhibitory processes are deliberate and effortful, while others occur automatically. For instance, in the Stroop task, participants must name the color of the ink rather than read the word itself. The automatic response to read the word must be inhibited, a process that engages cognitive control consciously. Yet certain priming tasks reveal that inhibition can also be triggered without conscious awareness, suggesting that inhibitory mechanisms are deeply embedded in both conscious and unconscious domains of cognitive function. Current research is also exploring the plasticity of inhibitory systems. Functional and structural neuroimaging studies show that repeated engagement in tasks requiring cognitive control can induce neuroplastic changes in the physi and its networks. This suggests that inhibition, like other cognitive functions, can be trained and improved over time. Digital training tools and gamified cognitive tasks are being developed and tested for their ability to enhance executive function, particularly in populations with cognitive deficits. The growing field of computational modeling has provided further insight into the dynamics of cognitive control and inhibition. Models such as the interactive race model of the stop signal task propose that go and stop processes race against each other, and whichever process finishes first determines the behavioral outcome. These models not only clarify the temporal dynamics of inhibition, but also inform the design of interventions aimed at improving inhibitory control. And in sum, cognitive control and inhibition are central to the regulation of thought, behavior, and emotion. They enable individuals to navigate complex environments, pursue long-term goals, and adapt to changing contexts. Their influence spans across developmental stages, psychiatric conditions, and domains as diverse as education, creativity, and moral decision-making. Ongoing research continues to reveal the intricate neural, cognitive, and behavioral mechanisms underlying inhibition, as well as strategies to enhance it in both healthy and clinical populations. Understanding and leveraging these mechanisms holds significant promise for improving human functioning across many dimensions of life. Cognitive biases are systematic patterns of deviation from norm or rationality in judgment, which occur due to the brain's attempt to simplify information processing. These biases are a consequence of the brain's reliance on heuristics, mental shortcuts that are efficient and usually correct, but prone to errors under certain conditions. Although heuristics are essential for navigating the complexity of daily life, their inherent limitations can lead to skewed thinking, flawed decisions, and persistent misjudgments, even among highly educated individuals. The study of cognitive biases lies at the intersection of psychology, behavioral economics, neuroscience, and decision theory, and has profound implications in domains ranging from clinical medicine to financial investment, legal systems, and public policy. The concept of cognitive bias gained prominence through the groundbreaking work of psychologists Amos Tversky and Daniel Kahneman in the 1970s, whose research demonstrated that human reasoning under uncertainty often departs with principles of formal logic and probability theory. Their seminal work laid the foundation for what is now called behavioral economics, a discipline that integrates psychological insight into economic models of decision making. Central to their research was the idea that humans are predictably irrational. Their decisions and judgments systematically diverge from what would be expected from a rational agent. These departures are not random, but structured in consistent, identifiable ways that can be studied and anticipated. There are over 180 documented cognitive biases, each influencing thought in subtle or overt ways, but a few have gained notable attention due to their prevalence and impact. Confirmation bias, for instance, is the tendency to search for, interpret, and remember information in a way that confirms one's pre-existing belief. This bias can severely distort reasoning processes by reinforcing erroneous beliefs and resisting corrective evidence. In an academic or scientific context, confirmation bias can lead to selective citation, biased data interpretation, and even flawed experimental design. It undermines objectivity and intellectual humility, often acting as a barrier to genuine learning or paradigm shift. Another common bias is the availability heuristic, where individuals judge the probability of events based on how easily examples come to mind. This can lead to exaggerated fears about rare but vivid events, such as plane crashes or shark attacks, while underestimating more statistically probable risks like car accidents or heart disease. Media coverage heavily influences this bias by disproportionately representing rare, dramatic events, creating a feedback loop that amplifies public misconceptions. For professionals in health communication or public policy. Recognizing the availability heuristic is crucial in crafting interventions that align perception with actual risks. Anchoring bias is yet another influential error in judgment, where people rely too heavily on the first piece of information encountered, the anchor, when making decisions. This bias is widely exploited in marketing, negotiations, and pricing strategies. For example, the initial price listed for a product serves as an anchor that shapes consumer willingness to pay, even if it bears no relation to intrinsic value. Similarly, in legal settings, initial sentencing recommendations can anchor judges' final decisions, potentially skewing justice. Overconfidence bias, where individuals overestimate their own knowledge, abilities, or control over outcomes, is particularly pervasive in expert domains. Professionals with high levels of training may assume their confidence correlates with accuracy, leading to diagnostic errors in medicine or miscalculations in engineering and finance. Interestingly, research suggests that experts may be just as susceptible to overconfidence as laypersons, especially when feedback is delayed or ambiguous. This reveals a critical tension in professional domains. Expertise fosters competence, but may also breed complacency or blind spots unless continuously challenged. Cognitive biases also play a crucial role in group dynamics and social cognition. The in-group bias causes people to favor members of their own group over those of others, which can reinforce social divisions and lead to discriminatory behaviors, even in the absence of explicit prejudice. Similarly, the halo effect leads to the assumption that someone who excels in one domain will be equally competent in others, such as assuming that a charismatic speaker is also morally trustworthy. These biases contribute to the formation of echo chambers, polarization, and groupthink, particularly in high-stakes decision-making environments such as politics, law, or business strategy. From a neuroscientific perspective, many cognitive biases are rooted in the architecture of the brain, particularly in the interaction between the prefrontal cortex, which governs rational decision-making, and limbic structures of the amygdala, which regulate emotional. The tension between deliberative and affective systems creates fertile ground for cognitive distortion. For instance, when individuals are under stress, the brain shifts toward faster, emotion-driven processing, increasing the likelihood of biases such as loss aversion, where the pain of losing is psychologically twice as powerful as the pleasure of gaining. This can lead to risk-averse behavior, even when risks are minimal or potential gains are substantial, impacting choices in everything from investment portfolios to personal relationships. Efforts to mitigate cognitive biases are ongoing and complex. Awareness alone is often insufficient to correct for biases, as many operate unconsciously and persist even when individuals are trained to recognize them. Debiasing strategies include structured decision-making tools, algorithmic aids, and institutional checks such as peer review and adversarial debate. In clinical settings, checklists and decision support systems have been introduced to reduce diagnostic errors stemming from heuristic shortcuts. In finance, algorithmic trading has helped curb the influence of human emotion, though it introduces new forms of systemic risk. Even in the realm of artificial intelligence, there is growing concern about algorithmic bias, which often mirrors human cognitive distortions embedded in training data, highlighting that the challenge of bias is both human and machine-bound. The persistence of cognitive biases raises important ethical and epistemological questions. If human judgment is fundamentally fallible, what are the implications for concepts such as responsibility, free will, and expertise? How can institutions be designed to harness human strengths while protecting against systematic error? These questions invite a more compassionate and humble view of human cognition, one that acknowledges its limitations while striving for structures that promote better judgment through diversity, transparency, and continuous feedback. In sum, cognitive biases represent a central feature of human thought, not a flaw to be eliminated, but a reality to be understood and managed. They are the price of a brain evolved for efficiency rather than accuracy, capable of remarkable insights and yet prone to distortion. By studying these biases rigorously, we can design environments, systems, and cultures that anticipate and counteract their worst effects, transforming our collective cognition in the process. Artificial intelligence, AI, has rapidly transitioned from a niche area of computer science into a foundational technology transforming industries and societies. At the heart of its most ambitious goals lies the quest to replicate, simulate, or even surpass human cognitive processes. The cognitive aspects of AI encompass the theoretical frameworks, computational models, and philosophical underpinnings that aim to emulate intelligent behavior. That this effort is not merely technical, but profoundly interdisciplinary, drawing from psychology, neuroscience, linguistics, philosophy, and cognitive science, to build machines that can learn, reason, perceive, and act. The term cognitive refers to the mental processes involved in acquiring knowledge and understanding, such as perception, memory, language, problem solving, and decision-making. In artificial intelligence, these processes are mimicked through algorithms and architectures designed to replicate or approximate human cognition. Classical AI, often referred to as symbolic AI, began with the assumption that intelligence could be reproduced by manipulating symbols according to logical rules. This approach, influenced heavily by early cognitive psychology, emphasized structured representations like logic trees, semantic networks, and rule-based systems. However, symbolic AI had limitations, particularly in handling ambiguity, learning from data, and adapting to novel situations. This led to the emergence of connectionist models, such as neural networks, which draw inspiration from the structure and function of the human brain. These models process information in parallel and distribute it across networks of units, allowing AI systems to learn patterns from vast datasets, a capability particularly evident in deep learning. While these systems lack the transparency and interpretability of symbolic approaches, they have proven remarkably effective in domains like image recognition, natural language processing, and game playing. One of the central cognitive functions AI seeks to emulate is learning. Machine learning, a subset of AI, enables systems to improve performance through experience. Supervised learning mimics the human way of learning with guidance, as in a classroom setting, by using labeled examples. Unsupervised learning, by contrast, aligns more with exploratory learning, identifying patterns without explicit instruction. Reinforcement learning introduces a form of behaviorist learning, where agents learn optimal actions through rewards and penalties, mirroring how humans and animals adapt through trial and error. Each of these paradigms draws upon distinct psychological theories, showing how AI and cognitive science are mutually informative. Language is another cognitive faculty where AI has made profound strides. Natural language processing, NLP, allows machines to understand, generate, and interact through human language. Early approaches, rooted in symbolic representations, struggled with the complexities of grammar, context, and meaning. Modern NLP systems, powered by large language models like GPT and BERT, leverage deep learning and probabilistic models to capture semantic relationships and generate coherent text. While these models often lack genuine understanding, operating instead on statistical regularities, they nonetheless challenge traditional assumptions about the uniqueness of human linguistic competence. Memory, too, has cognitive and computational analogues. Human memory is not merely a static storehouse, but a dynamic system that integrates new information, prioritizes relevance, and reconstructs experiences. In AI, memory architectures have evolved from fixed databases to more flexible systems, like attention mechanisms and memory, augmented neural networks. These enable models to focus selectively on relevant inputs and retrieve contextual information, enhancing performance in tasks requiring reasoning or sequence prediction. Concepts like working memory and long-term memory have also found implementation in architectures such as systems, post-dominant memory networks, and transformers, which manage temporal dependencies in data. Reasoning and problem-solving, core domains of human cognition, remain among the most challenging for AI. Symbolic systems excel at deductive reasoning in constrained environments, such as mathematical proofs or logical inference engines, but often fail in open-ended or ill-defined contexts. Conversely, machine learning models can generalize from examples, but may lack the transparency and rigor of symbolic logic. Hybrid systems that combine symbolic and sub-symbolic elements aim to bridge this gap. These neuro-symbolic models seek to unify the strengths of both paradigms, potentially paving the way toward more robust and human-like reasoning capabilities. Perception, particularly visual and auditory, is another cognitive frontier where AI has made significant inroads. Inspired by the sensory processing of biological systems, AI models for computer vision and speech recognition translate raw input into structured representation. Deep convolutional networks, for example, mimic the hierarchical processing of the visual cortex, extracting increasingly abstract features from images. Similarly, recurrent neural networks and attention-based transformers model temporal sequences in speech and sound, enabling real-time transcription and language translation. But despite these advances, AI perception still lacks the depth of contextual awareness and multisensory integration characteristic of human cognition. A crucial philosophical and cognitive dimension of AI is the question of consciousness and intentionality. While current AI systems exhibit competence in specific tasks, they lack sentience or self-awareness. Cognitive science distinguishes between weak AI, which simulates cognitive processes, and strong I, which would possess genuine understanding and consciousness. The Chinese room argument, posed by philosopher John Searle, challenges the notion that syntactic manipulation of symbols constitutes understanding. It raises enduring questions about whether cognition can be fully captured by computation, or if something essential is missing, perhaps tied to embodiment, affect, or phenomenological experience. Embodiment is increasingly recognized as central to cognition. Human intelligence is not disembodied, but arises through interaction with the physical and social world. This has led to embodied AE, where robots with sensory and motor capabilities learn through situated experience. Such systems challenge the Cartesian divide between mind and body, aligning with theories in cognitive science that emphasize inaction, affordances, and sensory-motor coupling. Social cognition, too, has gained prominence, with AI systems being trained to interpret human emotions, intentions, and behavior. These developments suggest that truly general intelligence may require not just abstract reasoning, but embodied and embedded interaction. Ultimately, the cognitive aspects of AI reveal both the potential and limitations of our current models. While AI systems have surpassed human capabilities in specific domains, such as playing chess or analyzing large datasets, they still fall short in generalizing across contexts, understanding nuance, and engaging in common sense reasoning. This gap underscores the complexity of human cognition, a product of millions of years of evolution shaped by biology, culture, and experience. It also highlights the importance of interdisciplinary research, where advances in neuroscience, psychology, and philosophy continue to inform the development of more intelligent and adaptable machines. In synthesizing these diverse threads, it becomes evident that AI is not merely a technical endeavor, but a cognitive one. It challenges our understanding of intelligence, offers new tools for exploring the mind, and forces us to reconsider the boundaries between natural and artificial thought. As we build systems that increasingly resemble cognitive agents, the questions we ask about autonomy, agency, and understanding will define not only the future of AI, but our own place within a rapidly transforming cognitive landscape. Cognitive aging refers to the gradual and heterogeneous process through which cognitive abilities change as individuals grow older. Unlike pathological conditions such as Alzheimer's disease or other dementias, cognitive aging is a normal, albeit complex, aspect of human development. It encompasses a broad spectrum of mental functions, including memory, attention, processing speed, executive function, and reasoning. While some cognitive domains show marked declines with age, others remain stable or even improve. Understanding cognitive aging is crucial, not only for identifying what constitutes normal versus abnormal cognitive trajectories, but also for informing interventions that promote healthy brain aging and optimize life quality in later years. One of the earliest and most consistently observed cognitive changes with age involves a decline in processing speed. This refers to the rate at which individuals can perceive, integrate, and respond to information. Older adults often take longer to perform tasks that require rapid mental operations. While slower processing speed does not inherently equate to impaired cognition, it can compound challenges in other domains, such as memory and executive function, particularly in situations requiring multitasking or real-time decision-making. Working memory, which involves the temporary storage and manipulation of information, also tends to decline with age. But this is particularly evident in tasks that require active mental juggling, such as keeping track of multiple items or performing calculations in one's head. Episodic memory, which allows individuals to recall specific events and experiences, shows notable age-related decline as well. This often manifests as difficulty in remembering recent conversations, names, or where objects were placed. In contrast, semantic memory, the repository of general knowledge and facts, typically remains stable or may even improve, likely due to cumulative life experience and education. This divergence between episodic and semantic memory illustrates that cognitive aging is not uniformly degenerative. Executive function, encompassing abilities such as planning, inhibition, mental flexibility, and problem solving, may also be affected by age. Older adults often exhibit challenges in tasks requiring divided attention or shifting between cognitive sets. However, the extent of these changes can be highly variable, influenced by individual differences in lifestyle, education, health status, and even genetic predispositions. Importantly, not all cognitive functions decline with age. Vocabulary, emotional regulation, and crystallized intelligence, which involves knowledge acquired through learning and experience, tend to be resilient or even improve well into late adulthood. Neurological underpinnings of cognitive aging have been illuminated through advances in neuroimaging and biomarker research. Structural MRI studies reveal that aging is associated with reductions in brain volume, particularly in the prefrontal cortex and hippocampus, regions critical for executive function and memory, respectively. These changes are accompanied by decreases in white matter integrity, which can affect the efficiency of neural communication. Functional imaging studies have shown that older adults often exhibit altered patterns of brain activation, including greater bilateral activation of the prefrontal cortex, a phenomenon referred to as the Harold hemispheric asymmetry reduction in older adults model. This is interpreted as a compensatory mechanism where additional neural resources are recruited to maintain cognitive performance. On a neurochemical level, aging is associated with reductions in the availability of key neurotransmitters such as dopamine, acetylcholine, and serotonin. These changes can influence attention, learning, and mood regulation. Dopamine, in particular, plays a crucial role in reward processing and working memory, and its decline has been implicated in several age-related cognitive changes. Additionally, oxidative stress, inflammation, and vascular changes in the brain contribute to cellular aging and cognitive decline. Cerebrovascular health is increasingly recognized as a critical factor in preserving cognitive function, underscoring the importance of cardiovascular risk management in promoting brain health. Despite these challenges, cognitive aging is not a predetermined or uniform trajectory. The concept of cognitive reserve offers a compelling framework for understanding individual variability. Cognitive reserve refers to the brain's resilience to neuropathological damage, influenced by factors such as education, occupational complexity, social engagement, and intellectually stimulating activities. Individuals with higher cognitive reserve may exhibit fewer cognitive symptoms despite similar levels of brain pathology, suggesting that lifestyle interventions can modulate the impact of aging on cognition. Indeed, a growing body of research supports the efficacy of lifestyle factors in promoting cognitive health in older age. Physical activity, particularly aerobic exercise, has been shown to enhance neurogenesis, increase hippocampal volume, and improve executive function. Dietary patterns rich in antioxidants, omega-3 fatty acids, and polyphenols, such as the Mediterranean diet, are associated with lower rates of cognitive decline and dementia. Cognitive training and lifelong learning can also bolster specific cognitive skills and may delay the onset of age-related decline. Moreover, social engagement and emotional well-being contribute significantly to cognitive vitality, as chronic stress and social isolation have been linked to accelerated cognitive decline. Technological interventions and digital cognitive training platforms offer additional avenues for cognitive enhancement, though their efficacy remains a topic of active investigation. While some programs show promise in improving targeted cognitive skills, evidence for broad transfer to everyday functioning is still mixed. Nonetheless, they hold potential as accessible tools for maintaining cognitive engagement, particularly when combined with other healthy behaviors. Importantly, cognitive aging must be distinguished from pathological aging. While some decline in mental agility is normal, abrupt or severe deterioration warrants clinical evaluation for conditions such as mild cognitive impairment, dementia, or dementia. Early diagnosis can facilitate management strategies and access to resources that support autonomy and quality of life. Screening tools and biomarkers are becoming increasingly sophisticated, allowing for better differentiation between normal and pathological trajectories. Ethical and societal implications of cognitive aging are also significant. As populations age globally, there is an increasing need to design age-friendly environments, policies, and healthcare systems that accommodate cognitive diversity. Issues such as elder employment, driving, financial decision-making, and legal competency intersect with cognitive function and require nuanced consideration. Promoting cognitive health is not merely an individual concern, but public health priority that impacts societal productivity and intergenerational equity. In conclusion, cognitive aging is a multifaceted and dynamic process shaped by biological, psychological, and environmental factors. While certain cognitive functions decline with age, others remain stable or improve, highlighting the plasticity and adaptability of the aging brain. Advances in neuroscience and epidemiology have deepened our understanding of the mechanisms underlying these changes and point to actionable strategies for promoting cognitive health. By embracing a holistic and proactive approach, society can empower individuals to age with mental vitality and dignity.